now what we're doing, we're going to get onto a really interesting section. What we're going to talk about is something called hyperbolic functions. This is section 6.6. Some instructors cover this, some instructors choose to kind of gloss over it. We're going to cover it because I think it's really interesting, it's really useful. So we're going to talk about hyperbolic functions. You go, what in the world is a hyperbolic function? I'm going to show them to you right now. The hyperbolic functions, the reason why they're in this chapter, in this, this section here, right after inverses, is because hyperbolic functions they don't look a lot like, but they act a lot like trig functions. So we call them hyperbolic trig functions sometimes. So let me give you an example of what these things are. Here's the definitions for your hyperbolic functions. So we start with sine. To say that it's hyperbolic, we just introduce a little h. Some people call this sinh. Say sinh, because it's so easy. It's a cinch. I know, right? I'm a dork. I'm very possibly the largest dork you've ever seen. So, sinh, hyperbolic sine. Here's the definition of it. It's weird. It is e to the x minus e to the negative x over 2. What's really interesting about these things, you ever notice how when you drive next to like electric wires, how they curve like that? It's called a catenary. They're actually based on hyperbolic functions. So the way that a cable hangs between 2 points is based on some of this stuff. Really weird. It actually happens in real life. They use it for engineering all the time. So this is sinh, or hyperbolic sine, hyperbolic cosine, cosh. Looks really, really similar. Really, really similar. The rest of the hyperbolic functions stem from these two. So really quickly, if you wanted hyperbolic tangent, no special name, no tanh or anything like that. It doesn't really sound good anyway. Just hyperbolic tangent. Hey, now this is what's cool about this. A lot of the same properties of trig functions carry over to hyperbolic functions. So whereas tangent equals sine over cosine, hyperbolic tangent equals sinh over cosh. So this would equal hyperbolic sine over hyperbolic cosine. That's interesting. Imagine this over this, and that is what hyperbolic tangent is. I did it twice in a row. Come on, letter draw an S. In trig functions, cosecant is 1 over sine. Hyperbolic cosecant is 1 over sinh. That's right. Hyperbolic sine. Looks very similar. Same thing happens with secant. This is now 1 over cosh. And if hyperbolic tangent equals sinh over cosh, then hyperbolic cotangent is
cosh over.
Yep, it is the reciprocal. You guys okay with those properties?
Yeah.
Those are the definitions that we work with in these hyperbolic functions. Now, I'm going to give you some identities. The identities look really similar to the basic trig identities that you have, but there's slight differences. So write these down, have them next to you when you're doing your homework. That way you can refer back to them, okay? So write these down, and I expect you to memorize all of them. Some of them you're going to because they're just so similar to the other ones, but some differ just slightly, okay? So here's the identities that we're going to use. hyperbolic sine, if I plug in a negative x, it gives me now negative hyperbolic sine. What this is saying, and you can write this down next to it, this is saying that just like sine is an odd function, you remember odd? Odd is symmetrical about the origin. Just like sine is an odd function, hyperbolic sine is also an odd function. That's what this says. Basically this says, hey, odd function. Now cosh. Think back to cosine. Is cosine even or odd? It's actually even because it's symmetric across the y-axis. Cosh when I plug in a negative actually gives you back the positive. That's saying this is an even function. If you need to look up odd or even, go ahead and look up what odd and even means later. Those are two identities for us. Now, this is where some of the differences happen. The Pythagorean identity for trigonometric functions, what would go here to give us 1? A plus would go there. For hyperbolic, it's a minus. This is why I'm telling you, have these next to your paper when you're doing it. Because right now these are brand new, okay? It's a little bit different. They're all hyperbolic. So they're a little different. Also another one, another Pythagorean. That one. It's also true. I'm just going to state the rest of them. Some of them are going to look really familiar to you. I hope they do. They're on those cheat sheets that I know a lot of you have when you in the back of your book or whatever, all the trig identities that you carry with you, and it's a good thing. This one's kind of an important one. This will look familiar to you. Remember this one? It's called the double angle. If you had this basic old sine without the hyperbolic, this would be equal to, do you remember it?
2 sine
Yep.
x.
2 sine cosine.
This would be 2 sine cosine.
Cosine.
Well, same thing happens here. It's 2 sinh cosh. That's kind of cool. That looks really similar. In fact, I'm going to prove this one for you in just a bit. Okay, I swear, this is it. I'm tired of writing too. Arms wore out already. Okay, I know that's a lot of them, but for those of you who are familiar with your trig identities, don't a lot of those look really, really similar to what you've learned?
Yeah.
A lot of them are very, very, very close. I mean, this one, exactly the same. These ones close. These ones exactly the same. I mean, they're all so, so close. Well, what I'm going to do now, you're not going to be required to do all of these proofs, but I want to give you an idea about how you would prove one of these. So let's take a look at Which one I say, that one? Let's take a look at that one. I'll prove that for you. So we're going to prove number 7. The way that you prove these, I know you're still writing, some of you, but the way you prove these, you start here on the left side, or start on one side and prove the other side, okay? You don't do them both at once. You start on one side and work to the other. So if I start with sinh of 2x, okay, follow me along here. The only thing we have to work with as far as proofs go are other identities, which is probably not a good idea right now since we haven't proved any of them, or these definitions. And these are the only 2 definitions that we have that go back to e to the x. So let's see what this would be. Please listen very carefully. I don't want to lose you right now. If sinh x equals e to the x minus e to the negative x, sinh 2x would be e to the 2x minus e to the negative 2x. Does that make sense? Whatever you have here is whatever you plug in there. So then this equals e to the 2x minus e to the negative 2x all over 2. Does that make sense? Let's rewrite it just a little bit. I'm going to rewrite this as e to the x squared. Is that still legal to do? Minus e to the negative x squared over 2. You okay with that one? That, my friends, is a difference of squares. Do you see it? Yes, no? Difference of squares can be factored. So if we factor that, this is e to the x minus e to the negative x times e to the x plus e to the negative x over 2. You still okay so far? Now, do those look similar to some of these other definitions? I'll make it, okay, I'll do one more step. See by the blank looks on your face that no, the answer is no, some of them don't. Check this out. What if I did e to the x minus e to the negative x over 2 times e to the x plus e to the negative x? Look back at our definition for this, please. How much is this?
Sine.
This is hyperbolic sine, or sinh. Is this cosh?
Yeah.
Oh,
Where's the 2?
Where's the 2? So, we're going to make a 2. Do you agree that I can multiply by whatever I want as long as I multiply by 1?
Yeah.
It doesn't change it. So, I'm going to multiply by 2 over 2. Only, I'm going to put this 2 here and this 2 out front. Did you catch that?
Yeah.
This one goes here, this one goes out front. It's very similar to your identities that you did with sine x over x when x approaches 0. And you had like sine of 5x over x, multiply by 5 over 5, and you get 5. So I multiply by 2 over 2, it's still 1, but now we have 2, this is sinh, this is cosh, and we've just proved it. So on some of your homeworks, they're going to ask you to do these. Go back to these definitions and use them. Some of them are pretty easy, pretty straightforward. This one's pretty straightforward. Did that make sense to you? It's different from anything you've probably ever done. Show of hands if you understood it, if you feel okay with it. Good, that's fantastic. Okay, so we've proved it, and that's not a problem. Now that we've done that, what I'd like to cover are the derivatives. We're going to do derivatives, we're going to do the integrals, then we'll start working through some of these examples and call it good. Do you have any questions on your identities? I'll be referencing them, but we're not going to do a whole bunch for today. I just wanted to prove them for you. We'll be using them in your derivatives and integrals. Any questions at all? Because I got to erase it. Okay, let's talk about your derivatives. I'd like to give you the first 3 just by some very simple proofs. That way you understand where these things are coming from. Tell me something first, though. What's the derivative of sine? Just sine. Okay, what's the derivative of cosine?
Sine.
Very good. And the derivative of tangent? We're going to see if there's any differences with these things. So let's start off with the derivative of sinh. How do you know it's cosh? Are we guessing? We're guessing. I looked in the book already. Well, let's go back to what the identities say. Okay, we'll prove it. So if I'm going to do this, keep in mind that what this is the derivative. I'm going to do derivatives very quick right now to prove these, okay? This would be the derivative of e to the x minus e to the negative x over 2. So we're going back to the definition. You guys okay with that? Derivative of e to the x, remember this 2, you do not need a quotient rule here. It's a constant. So derivative of e to the x is e to the x minus the derivative of this is e to the negative x times negative 1. See where negative 1's coming from? That negative would change us to a plus. This is, yes, the derivative of sinh is cosh. Isn't that kind of cool? Do you guys see the proof out of that one?
Yeah.
Interesting. Okay, so how about we do, now this one's going to blow your minds. Maybe. This would be the derivative of e to the x plus e to the negative x over 2. Check this one out. Firstly, notice that is cosh. What's the derivative of e to the x? Derivative of e to the negative x?
E to the x times negative.
Times negative, oh, so negative e to the negative x over 2. How much is that? Not negative, it's just sinh. Do you see it? So this one, just like regular trig functions. This one, not so much because we don't have the negative, but still the idea is very similar. Question?
Can you explain one more time why that 2 is constant? You don't use quotient rule? Because if I see that, I automatically do quotient rule.
Well, you shouldn't, because it's not a function of x over a function of x. It's a function of x over a constant. If you did quotient rule, hey, everybody, what's the derivative of 2?
Undefined.
No, not undefined. Half your quotient's gone. It's low d high, right? Minus high d low, d low. The second half of your quotient is 0. Why would you do that? Now that I just said you don't need a quotient rule, that's like okay, so from our definition, we know that this is equal to,
Now.
if I could write it correctly, yeah. Do we need a quotient rule here? Yeah, we do. Because, well, this is a function of x over a function of x. That's different, okay? Now, here's the nice thing about this. Because we just proved these two derivatives, we can use them. We don't have to change it into these. We just proved it. Do you got me?
Yeah.
So all we need is a quotient rule. Now I'm going to do the quotient rule really quickly. Quotient rule says low d high, which is cosh. Does that make sense? Low d high minus high d low. Square the bottom, and away we go. So low d high minus high d low, square the bottom, and we're good to go. Oh, let's see. That's cosh squared x minus sinh squared x all over cosh squared x. Look back at those identities I told you to have next to you at all times. Can you tell me how much this is? Exactly. 1 over cosh squared x. Now,
Can you just bring it up and make it secant?
now look back at your identities again. Your definitions. 1 over cosh.
Yeah, it's hard to say.
It is hard to say. 1 over cosh was hyperbolic secant. Does that make sense? So 1 over cosh squared is hyperbolic secant squared. So the derivative of tangent, hyperbolic tangent, is hyperbolic secant squared. Does that look similar to your trig functions? In fact, a lot of them are going to. I'm going to give you the list right now of all these things, and I'm going to likewise give you the integrals right next to them. We'll do that over here. This will need little cheat sheet thing, yes.
My cheat sheet
So
says-
here's your table, your new table of more derivatives and more integrals. Woo! The table's getting pretty long now, isn't it?
Yeah.
Table of D's and I's, derivative and integral. Please keep in mind what can happen every time you do a derivative. What can happen? Always. Always look for chain rules, okay? So, still chain rules exist. So if I'm talking since u, then that's going to be cos u, cost darn you, get it? Du dx. By the chain rule. What that means is that going backwards, the integral of cos u du would equal what?
Plus C.
If the derivative of sinh gives you cos, integral of cos gives you sinh. What's nice about hyperbolics, you have no negatives to worry about. Who cares? There are none. In sinh and cos at least, that's good to go. That's kind of nice. Derivative of cos u, we just found it out, was sinh u du dx by the chain rule. Therefore, the integral of sinh u is what, please? That's right.
Shouldn't that be you same?
Yeah, thanks. We already did tangent over here. If we do hyperbolic tangent, then our derivative is
Hyperbolic square.
good. Which means if I ever get the opportunity to make a hyperbolic secant squared, then we end up getting hyperbolic tangent plus c. Are you guys okay with these so far? The first three we've actually done already. The last three, they are going to look so similar to the things that you've done. Of course, some signs can be different, because as we found out with sine and cosine, that, well, the derivative of cos is not negative sine, it's sinh. So some of the same thing happened here. When we did cosecant, when we did derivative cosecant, you got negative cosecant cotangent, correct? Same thing we get here. So when we do hyperbolic cosecant, we get negative hyperbolic cosecant times hyperbolic cotangent. Du dx. Which means that our integral of hyperbolic cosecant cotangent, that's right, this is what we typically do with our integrals. We usually don't have the negative in here, we just say the answer, our resultant, is going to be negative. Which one am I missing?
Secant.
Secant, okay, secant. Let's do secant. The derivative of a regular secant is secant tangent. The derivative of hyperbolic secant is hyperbolic secant, hyperbolic tangent, but it's negative. Notice how some of the signs change. which means that if I have a hyperbolic secant and hyperbolic tangent, we're going to get negative hyperbolic secant. Okay, one more. I swear, I know it's dry. I really do. We're going to practice some in just a bit. I do know this is dry. What's the last one? What one is that normally? What is the derivative? Negative cosecant squared. So when we do hyperbolic cotangent, we end up getting the same thing. We get negative hyperbolic cosecant squared. It's hard to say, isn't it? How there's so many hyperbolics in there and stuff. So negative hyperbolic cosecant squared. Of course, du dx by our chain rule. Which means when we get an integral with the hyperbolic cosecant in there, hyperbolic cosecant squared in there, we know that that's going to be equal to negative hyperbolic cotangent. Whew, oh my gosh. Okay, that's it. Make believe. Do yourself a favor. Keep these handy. Keep your identities and your derivatives and integrals on the same little piece of paper and keep them handy all the time, okay? Because we're going to be using them. Not a whole bunch. Like I said, a lot of this book doesn't depend on this section. It's kind of a little standalone section, but it's a good section. It is important in real life. I mean, this stuff does happen, so I wanted you to be aware of it. Now, we're going to practice. What we're going to find out is that your derivatives and your integrals, it really doesn't change from all the stuff that you've just learned how to do. It's going to be a lot of chain rules. It's going to be a lot of substitutions. You're just trying to make them fit. Now there's just more stuff that you can fit it into. Does that make sense to you? You don't have to make everything look like this to take a derivative. Now that we have all these, we get to use them. So that's cool and all. This is what they are. But we get to use this stuff, which is nice. You want to see some examples of this?
Sure.
Okay, so we are actually going to do a lot of derivatives. Let's do that. Okay, so cos squared, 3t squared plus 1 is the argument of our hyperbolic cosine function. Tell me some things that you see here. Tell you what, this is, never mind, I can't say that joke. Anyway, in this class, it's kind of like in Math C or your intermediate algebra class when the teacher asks you, what do you do here? And 90% of the time, you just have to say, factor, and you get it right. Here, if I ask you, what are you going to do here? 90% of the time, you say, chain rule. Yeah, you're going to get it right, okay? There's always going to be a chain rule involved. So if you don't know the answer, just say chain rule. You look like a genius.
So you couldn't do a substitution here?
Are you doing integrals?
Yeah.
Then you would probably not want to do a substitution. Technically, a chain rule is a substitution. Just don't show it. You substitute for u, you do it, you do du dx, okay? But that's the substitution is the opposite of a chain rule. Okie dokie, it's for integrals. Does that make sense? Now, I see a chain rule. In fact, I see two. You need to know that hyperbolic cosine squared, this means it's this squared. That's what that means. Did you know that?
Yeah.
That little 2 right there, it's the whole thing is being raised to the second power. We write it this to make it easier. So with our derivative, tell me the first thing we're going to do, please. Quickly, though. I know it's chain rule. Thank you for following my advice right now. I'm just yelling it out. Go ahead. 2 to the front. Okay, very good. So 2 to the front. Do we change the inside on chain rule? So this is going to be nasty. This is going to be cosh of nasty crap. Raised to what power now? And then we're done, right? No, no, we don't get off that easy. So we bring down the 2, leave it alone, subtract 1. Now we do a derivative. You know what? I made a mistake. Did you catch my mistake? This should be a t. My apologies. Shame on Mr. Leonard. So bring down the 2, chain rule. Just a general power rule if you know it by that name. Bring down the 2, subtract 1, keep the inside the same. Then you multiply by the derivative of,
The arc.
yep, the inside of that.
Oh man, it's
Another
another.
chain.
There's 3 of them in one.
Okay, so now we have this one. What is the, follow the DDT. The DDT tells you where you're doing calculus. Here, calculus said, just do the big thing first, chain rule. Okay, now we got that. Now do this thing. What does that say?
Cos 3t plus 1.
I know what it says. What are you gonna do?
Oh, since.
Derivative of this, so that's gonna be negative sinh or positive sinh? That's right, very good. So
Oh, yeah,
do you do the derivative of this right now?
No.
Chain rule says you leave that alone, and then you do the derivative of the inside later. Oh my goodness, let's do a 10-second recap, make sure you're okay with it. Does it look any different than your normal derivatives? It's just a slightly different idea because you're not dealing with trig, you're dealing with hyperbolic functions. So bring down the 2, no problem, it's chain rule. Derivative of this, that's sinh, leave the inside alone. Derivative of the inside, we're almost done. Derivative of this is, so this becomes 6t. Let's just rewrite it. So what I'm going to do is I'm going to pull this 6t out front, mash it together with this 2. Is this okay with you?
Yeah.
Yes.
So we're going to get 12t. We are going to get cosh 3t squared plus 1 times sinh 3t squared plus 1. Make it that far, you're good to go. Show of hands if you're okay with that one. Notice how the derivative ideas, the chain rules, they don't differ. They're the same. It's just that we have some different derivatives that we're dealing with. You okay with that one? Tell you what, let's. I'm going to try to get to 2 more. We'll see if we have time for that. Actually, you want to try one just on your own?
Yeah.
Sure, I think you can do it. Oh yeah. I want hyperbolic cotangent of, hyperbolic cosecant of 2x. Yes! I'm going to give you enough time as I erase this side of the board, and then we're going to go for it. Actually, you know what? Your dribs are up there, so I'll leave it for this one. Did you do the first step already? Thank you. What is your first step? What's the answer 90% of the time in this class?
Chain rule.
Hey, at least when you're dealing with derivatives. Yeah, we're going to do a chain rule. Do you guys see the chain rule inside of the chain rule?
Yeah.
This has, of course, a chain rule. This has another chain rule. So when we do it, well, it says take the derivative of the outside function. If I look over there, I see it's negative hyperbolic cosecant squared of the inside. So I'm going to leave this alone. Did you make it that far? Derivative of this is this. Leave the inside alone. It's chain rule. But then don't forget to multiply by the derivative of the inside. So chain rule says derivative of outside function, leave inside alone. Then multiply derivative of the inside function. Thankfully for us, that's a really easy chain rule. That's nice. What's the derivative of this? Sinh 2x, and then
Times the derivative of 2x.
times derivative of 2x. So we're going to get a 2 out of that. Okay, derivative. So this is done. We did derivative outside, leave inside alone, times derivative inside. We got this. We're following the ddx here. Now chain rule again. Derivative outside is leave the inside alone times the derivative of the inside. That's where we're getting that 2 from. You guys okay with that one?
Yeah.
Mash all this stuff together if you can. The 2, let's put that up front. So negative 2 hyperbolic cosecant squared of
Cos
2x
times sine h.
sinh 2x. Let's make sure we know that these are arguments of our hyperbolic functions. Take a deep breath.
That's a mouthful.
It's crazy. Show of hands feel okay with that one. Good, all right. Tell you what, we got time for one more. And next time, just to blow your minds, we're going to talk about inverse hyperbolic functions, all right? But not this time. Not this time, don't worry. I know, right? Oh my gosh. Just got through this. Let's try. Let's see, which ones? I'm going to erase all this because we're going to do an integral. Oh, don't worry, we're doing integrals. So we'll need this stuff.
How would you say that?
Cos h.
Yeah. Or cos. Or hyperbolic cosine inverse. Inverse. It's super fun to say.
Makes you sound real smart.
It does. Yeah. Imagine if you would have seen this the first day of class, huh?
Alpha picture.
What? See ya.
Later.
See ya.
Major.
No more math for me ever.
Go back to it. Listen.
Okay, we're going to work through it together. I'll give you some hints on this one. I don't have enough time to really have you work on it, but I'm going to show you some of the ideas here. One of the ideas is none of these things have a 3x in them. They'll have u's, or you can just make it an x, just a single variable. So anytime you see an argument with like a 3x, 3x, 5x, 5x, x squared with an x out front, just substitute. Do a very quick substitution to get rid of the 3x. So what I mean is we would do u equals 3x. So then we'd have du over 3 equals dx, or the 3 goes up front, whatever you want to say there. So we get cos squared u, sinh u, and then du over 3. Does that make sense to you? Yeah. No pun intended. But we have the over 3. We'll just pull that 1/3 out front. Now we can deal with this a little bit better. So basic substitution. Remember, you can substitute as long as you match up disregarding your constants. So if the derivative is 3, man, you're good to go. Get rid of the 3x. Pull this out front, we get 1/3 integral cos squared u sinh u du. Now, does this look exactly like one of these?
No.
Then what are you going to have to use?
Identity.
Not identities.
Substitution.
What do you use in integrals when it doesn't look exactly the same? You use substitution. So it's going to be a double substitution here, okay? Well, think about that. You have to, don't you? Don't you have to? It doesn't look anything like that. There's no identity that lets you put these together in any fashion, so you need a substitution. Now, substitutions work this way. Listen carefully, please. Substitutions work this way. The substitution is typically the inside of something, and the derivative has to be there. So let's look at the correct choice. Is this the correct choice for substitution?
No.
Cosh would be there, but not cosh squared. That's a problem. Is this the correct substitution? With the squared or without?
Without.
Good. It's the inside. So what we're going to do here is we're going to pick a different letter, like W, and pick that for cosh u. Make sure your dw matches your w. What's the derivative of cosh u?
Sine.
Sinh u d. Hey, look at this. This is exactly this thing. So when we change this, I'm going to have 1/3. Please watch carefully. This was cosh u squared. I substitute for cosh u. What goes here?
W squared.
Very good. That's w squared. This is w, so now we have w squared. You guys okay with that one?
Yeah.
That's gone now. What happens to all of this stuff? What is that? These have to match. Now look at that. Can you do that integral? That is an absolute piece of cake. This is going to be 1/3 W cubed over 3. We haven't done one of those in a really long time, have we? Quite forgot about those. We're doing all this trig stuff. You guys okay with that? Add 1 divided by the new exponent.
Yeah.
So W to the third over 3. That means we get W to the third over 9. And then we leave it like that?
No, yeah, so it's two, everything's like,
Everything. So here's the deal. So we've got W cubed over 9. What is our W? So then here we've got cosh, wait a minute. Cosh, cosh, you can put one of two things. U, or you can do the 3x. I'm going to put the U so I give myself 2 steps here. Over 9. Do I have it right?
No.
What am I missing? So this was our W. If we have W cubed, we need cosh cubed of U over 9. And now last little step, I'm going to erase this here. Last little step to make it final. We're going to have cosh cubed. Instead of our U, what was our U?
3x.
Over 9 plus C. Wrap it up. Did that make sense to you?
yeah.
So you can do a double substitution, just pick a different letter. But you'll see it's the same stuff you've been doing. It really is. Same derivatives, same integrals. It's just we have a new integration and derivative table. Show of hands feel okay with that one. Okay, obviously. All right, so last time we talked about hyperbolic functions. Now, if you think about hyperbolic functions, I know I didn't show you the graphs of them, but you can look them up. It's actually in your book. It's a one-to-one function. They're all one-to-one functions, which mean that if we have a one-to-one function, there has to be some sort of an inverse to it. So what we're talking about today are, okay, hyperbolics are one-to-one. We're going to talk about inverse hyperbolics. Here's the notation for it. It's just like any other inverse. We have, hey, hyperbolic function, now it's an inverse. All these are hyperbolic inverses of the normal hyperbolic functions that we talked about last time. I've given you the domain for each of them. You can go ahead and write that down. Like I said, we're not going to work a whole bunch with this stuff, but I want you to be aware that they exist. Obviously, they have to because they're coming from one-to-one functions. Now, what I'm going to talk about specifically here is what they look like as logarithms. You're like, wait a minute, as logarithms? Well, think back to what hyperbolics are. Hyperbolic sine was e to the x minus e to the negative x over 2. You with me? Now, what's the inverse of e to the x? It's a log. It's ln x, actually. Does it make sense to you? So if the inverse of e to the x in exponential is a logarithm, ln x, for instance, well, then the inverses of hyperbolics, because they're all based on exponentials, like e to the x minus e to the negative x over 2, and e to the x plus e to the negative x over 2, because they're based on those, well, then we can write these inverses also as logarithms. I'm going to show you that right now. So here's how these things look as logarithms. These are definitions. You can take them for granted. So if we want to write sine, hyperbolic sine inverse, you could also write it as ln x plus square root of x squared plus 1. Wherever you see this, it means this. Wherever you see this, you can actually write it as this. They're the same thing, they're definition. Now, tan, hyperbolic tan inverse. You can write that as 1/2 ln 1 plus x over 1 minus x. And last, we're only going to do 3, because the other ones you can find as reciprocals of these 3. So it's kind of easy just to define these 3, okay? The last one, well, this one's going to look a whole lot like sinh inverse. So this is cosh inverse would be ln x plus square root. Instead of x squared plus 1, we're going to have x squared minus 1. Just the difference of one little sign in there. Please write those down correctly. Make sure you have them exactly the way that I have them on the board. I don't want you to write these down and then write them down correctly and then use it wrong for the whole class, okay? You guys okay with this so far? Do you want to see a proof?
Yes.
I'm not going to prove all 3. I'll prove these 2 are very similar, so I'll prove this one. That way you get another one basically for free. So here's a proof for this. Let's start with cosh inverse x, and let's have it equal to, let's say y. Well, from what we know about inverses, I'm going to go through this a little bit quickly, but write it down if you want to. You don't have to memorize this proof. Just kind of, I want you to follow it, all right? So if I'm going too fast for you to write it down, just review the video later, or don't really worry about it. I just want you to be aware of it, understand where this thing comes from. You guys with me? So here we go. If this is true, then this has to be true. True? Sure, that's kind of the definition of inverses, right? Cosh inverse of x equals y if and only if cosh y equals x. Well, let's use the definition then for cosh y. If you remember this from here, I'm going to switch these sides, okay? Then x would equal, instead of cosh y, the definition of cosh y is e to the x plus e to the negative x over 2. Do you remember that? That's how I initially gave you these things. Oh, you know what? I made one mistake. Did you see the mistake? I actually made it. The y instead of x. I do this all the time because we memorize it as x. But if I'm going to say this is cosh y, then this has to be y and this has to be y. Did you guys catch that one? Okay. Now, since we have x equals, well, let's remember we're not actually doing derivatives here. This is just we're not doing derivatives at all. I didn't say the derivative of this equals this. Did you notice that? It's not derivative, not calculus. I'm saying this literally equals this. So we're not going to do any calculus at all. We're basically going to do some algebraic manipulation, trying to solve this thing for y. If we can solve this thing for y, look at the board here real quick. If we can solve this for y, and y equals this, then we'll have an expression in terms of x that represents cosh inverse. Does that make sense to you? So no calculus, no derivatives, nothing like that. We're just solving this. Well, one idea that we're going to do here, we're going to say, all right, well, this is cool. What if we just multiplied both sides by 2? Then we get 2x equals e to the y plus e to the negative y. All right. Now I'm going to do something here, because I'm going to manipulate this function a little bit, or this equation. I'm going to solve this for 0. So I'm going to subtract 2x on both sides. So I'm going to get 0 equals e to the y minus 2x plus e to the negative y. You guys okay with that so far? Now I'm going to do some fancy pants math. The fancy pants math here is this. I don't like this negative y. I don't like e to the negative y. So what I'm going to do to get rid of this, I'm going to multiply both sides of an equation. Keep in mind it's an equation I can do whatever I want as long as I do it to both sides. I'm going to multiply both sides by e to the y. If that's the case, e to the y times 0 is still 0. Only here, this e to the y will distribute. Check this out. I'm going to get, watch, e to the y squared. Do you see it? I'm actually going to keep it this way. E to the y squared. I'm going to get minus 2x e to the y. Minus 2x. I'm also going to write this a little bit specially. I'm going to keep this in parentheses. You'll see why in a second. Minus e to the y. And then, oh, look at this. If I have e to the negative y times e to the y, that's going to create e to the 0, or 1, plus 1. So everything should feel okay with that one so far. So we're just distributing. We got 0 here. We've got e to the y squared. We've got minus 2x e to the y. We've got plus 1. Because e to the negative y times e to the y gives you e to the 0. That's 1. So far, so good?
Yeah.
Now look at this carefully. This is kind of cool. This is actually a quadratic. Do you see it? Where a, the coefficients a is 1, b is negative 2x. I know it's weird, but we're going to use an x here. And c is 1. You with me? So, what we know from the quadratic formula is whatever I'm going to treat this thing like my variable. You can use a substitution and say, hey, let's make u equals e to the x, or sorry, e to the y in this case. Then you'd have u squared minus 2xu plus 1. Do you guys see that? And we'd have u equal to whatever my quadratic is. I'm going to eliminate that step. I'm just going to say, okay, well, because e to the y is what my term is, I'm just going to have e to the y. And then perform the quadratic formula. So the quadratic formula says negative b. Negative b. So negative this would give me positive 2x. You guys okay with that one? Plus or minus. Radical. B squared minus 4 times A times C all over 2 times A. So this is negative B, hey, negative B. Sign change because I'm taking the opposite of that. So negative B, plus or minus square root, no problem. B squared, this thing squared is 4x squared. Minus 4 times A times C, A is 1, C is 1, so we get minus 4. All over 2. We okay with that so far? Okay. So let's keep on working on that. What are some things that you could do here? I can cross these out right now?
No.
Heavens no. That's a plus and a minus. That's double wrong, all right? Plus and a minus. Jeez. It's okay in here, maybe in here. Factor the 4. 2x plus or minus. This is going to be the square root of 4x squared minus 1. You see it? Square roots work like this. When you have products, you can take the square root of the first factor times the square root of the second factor. So the square root of 4 is actually 2. So e to the y equals 2x plus or minus 2 square root of x squared minus 1. All over, I've got my 2, all over 2. Now tell me something you can do. You could break up the fraction. I'm not going to. Factor the 2's, yeah. If I factor these 2's, we get 2 times the quantity, x plus or minus square root of x squared minus 1, all over 2. Now can I simplify my 2's? Now it's appropriate. You can't simplify unless you have factored. Everything has to be multiplied together. These are gone. So, e to the y, working over here now, is x plus or minus square root of x squared minus 1. Now, I want to talk about the plus and minus real quick. A couple little notes here. E to the y has to be positive. Do you agree with that? Exponentials are always positive. The domain our domain is 1 to infinity. That we're working with here. Here's the problem. If I plug in numbers from 1 to infinity, most of them are going to be negatives. Most of this is going to be negative. So I plug in numbers like 5 or something. If I did that, 5 plus, I'm good. But 5 minus, I'm not good. This would be 5 minus the square root of 25 minus 1, the square root of 24. This would give me negatives, which does not fall inside my domain. Does that make sense? So for that reason, it's really not defined for this. So we're going to take that out. So e to the y, because of our domain, we can't have that. E to the y's got to be positive, and if I plug in numbers in here, this part, the minus part, this would not work very well. This right here would give us negatives, and we know that e to the y has to be positive. Does that make sense to you? So we omit the minus. Instead, we keep just the plus. And we're almost done. How do we get rid of the e? How would you do that? Yeah, if I take natural log on both sides, then ln of left side equals ln of right side. Do you see it? That goes away. We get y equals ln x plus square root x squared minus 1. And last, let's look back at what y is, what we defined y as. Y is actually cosh inverse. So, make a little substitution. Cosh inverse of x is now ln x plus square root x squared minus 1. And that is our proof. Show of hands if you feel okay with that one. Did you follow that? Fancy pants math, right? You know what we use? It was nothing really fancy actually. It's all algebra, all of it. No calculus. What? Do you see any derivatives? See any limits? No. It was all algebra, and it's really just quadratic formula. That's it. Just quadratic formula, and you work it all the way down. Take an ln on both sides, and you're good to go. The rest of them can be proved likewise, similarly. What I want to talk about now, if there's no questions, I want to talk about derivatives. Do you guys have any questions on the proof? I'm not going to make you do the proof. I think they have an example in the homework where they have you do the other one. If you did this one, can you guys see it's going to be almost exactly the same? Only thing that's going to be different is that's a minus, okay? Works exactly the same. That's the idea. What I want to do now is I want to talk about derivatives of these guys. I'll prove one derivative. I'll list the rest of them. We'll do a couple examples, and that'll be basically it for this section. You okay? Any questions? Do you need this stuff? Do you have it written down? Good. Which one did we prove? Let's stick with that one. Let's find the derivative of this Cauchy inverse. Let's do that. So remember that. So what we know is that we just proved that hyperbolic cosine inverse is equal to ln x plus square root x squared minus 1. So we know that for a fact. Here's the deal. What I want to do right now is I want to start finding out the derivatives of these things. What is the derivative of Cauchy inverse? How do we find that? Well, maybe we can do it right here. Since we have a definition, we should be able to do that. So, tell you what. Let's take a derivative on both sides. That'll give us derivative of Cauchy inverse equals, well, because that's a function of x, it's ln. Do you know how to take a derivative of ln? Yeah, now we can take derivatives of these things. So since we know the definition of it, these shouldn't actually be very hard at all. So if I want to find out derivative of Cauchy inverse, it's actually the same as the derivative of this nasty piece of junk. You know what I want to do? I want to see if we can, if we remember the derivative of ln. So we're going to do this kind of like an exercise. I want you to do the derivative of this thing. See what you get. So go for it. You should know how to do derivative of ln, right? Do it. Go for it. Do you see any chain rules? Always. So derivative of ln. 1 over the inside times the derivative of the inside. So derivative of ln. 1, here's our inside. 1 over the inside. This is by the chain rule. So 1 over this times the derivative of the inside. Remember what I told you about derivatives? Let the d dx tell you where the calculus is. 1 over inside times derivative of inside. We're done with calculus here. Did you guys make it that far? Did you all do that one?
Yeah.
Cool. Many of you are getting really fast at derivatives, which is great. So what's the derivative of x? By the way, what's the integral of 1? Okay, keep that in mind when you're doing these integrals. If you get integral of dx, that means integral of 1 dx. That becomes an x. Okay, just some people had a little issue with that, so I want to make sure you guys know that. So derivative of x is 1, not 0, it's 1, plus, I'm going to do this one in my head. Hopefully you get the same thing. This becomes a 1/2, so you bring down the 1/2. You would have leave the inside alone to the negative 1/2 because you subtract 1. And then by the chain rule, by the way, those brackets are important. By the chain rule we have, by the chain rule we have what? Derivative inside, that's right. We'd have the 2x. I want to know if you made it down that far. Show of hands if you did. Did you get that? If you didn't follow this the first time, remember that this derivative is 1, no problem. You can do these derivatives separately. So this is x squared minus 1 to the 1/2. Bring down the 1/2. Leave the inside the same. Subtract 1. Derivative of the inside is 2x, and that's our appropriate derivative. Now we're going to make it a little bit prettier. So tell me something that you see here. Twos are gone. Like it. Okay, so let's pretty this thing up. We got 1 over x plus square root of x squared minus 1. That hasn't changed in a while. We're going to have a 1 plus. Here's our 1 plus. X over the square root x squared minus 1. Make sure you have brackets or parentheses or something.
Wouldn't you multiply the x by both the 1 and the, never mind. It's
Okay.
internal.
You guys all right with that one? Now, this looks pretty bad. And if I gave you for a formula for if I gave this to you as a formula for a derivative, you'd be like, I'm sorry, what now? So no, we're going to make this thing prettier, all right? How we make this thing prettier is, there's two terms here. Let's make them go together for one term. Let's make one fraction out of that. Can we do that? Which is really easy because it's 1. We're going to have square root of x squared minus 1 over square root of x squared minus 1. So let's do that. Square root x squared minus 1 over square root x squared minus 1 plus x over square root x squared minus 1. If you didn't follow this, this is exactly the same. Is this still equal to 1? This is still 1. Yeah, absolutely. So all we're doing is writing that as this fraction so that we have a common denominator. I'm going to move over here now. So with that in mind, well, now we can make this one fraction. So we're going to have 1 over nasty stuff times worse nasty stuff. Square root of x squared minus 1, and then plus x, all over square root x squared minus 1. Okay, one show of hands, you can follow me that far. So remember, this is a proof right now. Obviously, you're not going to do this every single time you get a derivative of cosh inverse. You're going to do what I'm about to give you. Now, do you see why we made it nicer? Do you see anything that helps us here? I hope that you do. Do you see it? Do you see that this and this are identical by the commutativity of addition? They're exactly the same. They're gone. Which says that, let's go back to the beginning. We had the derivative of hyperbolic cosine inverse of x. And we worked on the right-hand side with this logarithm all the way down, and we ended up finding this is 1 over square root x squared minus 1. And that is our first formula for derivatives. So this one actually works. If we have cosh inverse of x, we know the derivative of cosh inverse x is 1 over square root x squared minus 1. Do they look really similar to your hyperbolic functions? They're going to be really similar, all right? Really similar. Because they come from the same idea of logarithms, which you're going to get the 1 over jump times derivative of jump. So since they're all defined as x's and square roots, we're going to do the same thing. So that's the first one. By the way, there's another way to prove this if you want. Do you want another way to prove it, or is this good?
Sure.
Another way? Yeah, I'll give you another way. If you did it this way. So, or, different type of proof. Just for funsies. If y equals cosh, and I'm going to go really fast on this one, cosh inverse of x, this only happens if x equals cosh y. If I take a derivative on both sides, by the way, keep this in mind, we're going to use it later. If I take a derivative on both sides, this becomes 1. This right here, we actually know the derivative for cosh y. Do you remember what it is? Sinh y. That's right. Times dy dx. Because we got the chain, you guys okay with the chain rule? So we get the chain rule. So if we solve for this thing, then dy dx equals 1 over sinh y. I'll just divide that by divide that on both sides. Now, because of our definition, let's see. That, right? Equals this. So working from here, if we wanted to solve for this guy right here, what I'd probably do is I'd add this and subtract 1. So cosh squared y minus 1 equals sinh squared y. You guys okay with that one? Okay, take a square root. This is an identity I gave you like the first day we had this stuff. Do you remember that one? Hopefully you do. Look at the video if you didn't. It's the very beginning video. Take a square root on both sides and we get sinh y equals square root cosh squared y minus 1. I switched sides and took a square root. And that's exactly what this thing is. Only think back to what cosh y equals for us. Cosh y is how much? How much? It's x. So then sinh y equals square root of, from here, x squared minus 1. And that solves it for us again. So 1 over square root x squared minus 1. Same thing, different way to prove it. This one's a little bit more direct. This one uses a different proof that we've already had in class, but it's faster. So one's kind of shortcut proof, one is the long proof stemming directly from the definition of what sinh inverse is. Do you guys follow both of them? Good for you, that's fantastic. Now, let me give you the rest of them. So, we know that if I do a derivative of cosh inverse, we end up getting 1 over the square root x squared minus 1. I'm just going to give you the rest of them. I'm not going to prove the rest of them. Some of the proofs are similar, some are a little bit different. But here we go. Hyperbolic sine inverse. Oh, you know what? Can I do something for you to show you that these are going to be, obviously, what are you going to use with a lot of these derivatives? What's the answer 90% of the time when I ask you? Okay, good. Yeah, you're going to use chain rule on a lot of these. So I'm going to change them to u's, just so you recognize that we're going to do chain rule a lot. So if we have, let's see, hyperbolic sine inverse, we have 1 over, sine and cosine look at this really similar all the time, especially with these hyperbolics. So we have 1 over square root u squared plus 1 du dx. If we want hyperbolic tangent inverse, we end up getting 1 over 1 minus u squared du dx. If we want hyperbolic secant inverse, we get negative 1 over u, then square root of 1 minus u squared du dx. Are these looking familiar to you? They look so much like the hyperbolics, which is why I said, hey, write these on a note card, make sure they're all right, that way you can look at them when you're going through your work, okay? If we want hyperbolic cosecant inverse of u, it's going to look just like this one, only, let's see, oh, you know what, I'm sorry, I read that wrong. No, I didn't, I read it right. Thought I made a mistake. Very similar, we're going to have u squared plus 1. And lastly, hyperbolic cotangent inverse, we got which one?
Tangent.
Hyperbolic.
So tangent and cotangent are the same.
Yeah, let me check on that.
It says in the book too.
It is, right?
Yeah.
It's exactly the same,
Okay.
which is really weird. But yeah, you get the same thing. Let's think about why. Stemming from the definition of, yeah, that would be. That's interesting. Check one more thing for me. One of these things has an absolute value, the other one doesn't. Which one is? Is it, do you know? Patrick?
Oh. The cosecant.
Cosecant has the absolute value, right? Okay. But the secant doesn't. Okay, good. I knew there's one little thing in there. It's a little weird thing. So what I want out of you, I want you to be able to use these things. They're just formulas for right now. So what we're going to do is we're going to do one example of a derivative. It's going to be really, 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 really similar to your hyperbolics, and that you're going to use chain rule a lot. All right, you're following the formula and then using a lot of chain rule. Make sure you have these down exactly like I've written them. Please double check this right now. As I'm double checking mine, I want to make sure that I got these right for you as well. That looks good. Yeah, we're all good. Okay, let me give you one example real quick. I'm sure you'd like an example, yes? Let's find the derivative of this guy. Let's go through it as a team. We're just going to do one example right now. Like I said, we don't use this a whole lot. And even if we did, you got your derivatives. They work really similar to your hyperbolic. So you have the formulas. You're going to have a little note card with that on them. No big deal. So let's go through and let's see if you see the way I see this thing. What's the first thing that you guys see on this?
Product rule.
Product rule gives away right there, correct?
Yeah.
Go ahead and do the product rule. So product rule says, no problem, we've been doing this since our last calculus class. Derivative of the first times the second plus the first times derivative of the second. So, let's see if we know this one. What's the derivative of e to the x?
E to the x.
So we're going to get this whole thing back again. E to the x, hyperbolic secant inverse of 3x. Nothing changes there. Plus, e to the x does not change. Let's look at this one. This is where you use this stuff. Right here, what acts as your u? What is your u?
3x.
So 3x is what we're going to put. Let's see, let's follow this down. We are here. So 3x is what you're going to put here, and what you're going to put here, and then you're going to square it. Did you guys do that?
Yeah.
If you didn't make it that far, can you follow me on this one?
Yeah.
So we're using this because it says hyperbolic secant inverse. Our 3x is our u. So u here, don't change any of this stuff, and don't forget chain rule here. So we've got -1. I'm going to write everything out. Not going to do a whole lot of math in my head here. 3x. Then I've got a square root. Then I've got a 1 first, then a minus, then a 3x squared. And then what? Good. This is where people forget a lot of constants. Right? I'm off by 3. Oh, where's the 3 coming? It's coming from right here. Or they're saying, wow, why isn't there a 3 up here? I got that 3. If something simplifies, okay? It's because you forgot the chain rule. So don't forget the chain rule. Make sure, I hopefully I've beat that into your head time and time again throughout this whole class. Chain rule, chain rule, chain rule. So we're going to do it a lot of times. So we keep on going. We got e to the x. Hyperbolic secant inverse of 3x. And then we've got an e to the x. We've got a -1 over all this stuff. Of course, we'll make that 9x squared times 3. Derivative of 3x is 3. Tell me some things that happen here. Gone and gone. That's multiplied. That's all multiplied. That's connected. That's fantastic. We'll make it a little bit nicer. What I'm going to do here is, instead of a negative, I'm going to make this a minus. I'm going to put my e to the x on the top of my fraction. and we get e to the x, hyperbolic secant inverse of 3x, minus e to the x over, let's see what's still there. What's still there? X is still there, and that's the whole thing.
You want to factor out the e to the x?
You could. If you factor out the e to the x, you have just hyperbolic secant inverse 3x minus 1 over this, and you could do that too. Show of hands feel okay with that one. Is it doable for you guys?
Yeah.
After dealing with the hyperbolics, yeah, it's not a big deal, okay? You just have 6 more formulas to really go through. Do you have any questions, comments, or anything at all? Are you sure? Are you ready to take a break from dealing with all this trigonometric and hyperbolic stuff for just a little bit?
Yay.
Now we're going to start section 6.7.
There's no integrals, we're not gonna.
Now we're just going to leave it right there, just kind of a fundamental level of approach on these derivatives. We're not going to get to the integrals, we're just going to do the derivative of these things, okay? Keep it light. This is pretty light, right?